Hello, this is problem 5 of the collection of 50 challenging problems in introductory dynamics that I'm collecting. And it's aimed for first and second year engineering students as well as physics students, those who take physics and mechanics, and also for those in high school, especially those who take AP Physics. This problem involves two-dimensional point mass kinematics. We have this skier who jumps from the edge and lands at this point. The speed is 10 meters per second. The launch speed is 10 meters per second. The launch angle is 9 degrees with respect to horizontal axis. And alpha is 11.3. Forgive my drawing, it's not quite much bigger, but the figure is not drawn to scale, but it is 11.3. So, and the problem asks us how far below the launch level does the jumper land, and how long would he fly? All right. The first step in every dynamics problem, mechanics problem, is to analyze the problem. What is it that the problem is asking us? It is asking us how far below the launch level. Let me give me a second. How far below the launch level does the jumper land? So jumper lands here. And how far, I'm not going to use a ruler, so just forgive my drawing. So how far below the launch level does the jumper land? Let's call this y. So y is what we are looking for. How far below the jump level or launch level does the jumper land? And we're going to assume that it's right at the edge. And then how long would he fly? Like, how long does it take for this skier to land at this point? So if so what I'm going to do is I'm going to call this point 1, and this is my point 0. Right. So you go from point 0 to point 1. All right. The way I explain every time I ask the students to think about it this way. If you don't know where to start, you should think about it this way. You should think about this as a 2D problem. All right, what is it that we know for 2D problems, for two-dimensional kinematics problems? What is it we know about them? Do we know, have we derived any relationship for example, the displacement? Have we derived any relationship for time, for velocity? This skier, once it jumps, is what kind of acceleration does he experience? So once he jumps, this is in vertical space. Therefore, the only acceleration experiences is gravitational acceleration on the Earth. So there is this gravitational acceleration, and the gravitational acceleration only points towards the center of the Earth, so it has only one component in y direction. So if I were to define a coordinate system here, this is my coordinate system, all right, and I call this positive, you can call it positive x, but I'm going to use positive I, and then I'm going to use positive j, meaning that my positive y-axis points up, or positive j-axis, and positive I points horizontally to the right. So what is our acceleration? Our acceleration only has one component, and that component points towards negative j, right? Because positive j points upward, negative j points downward. So if I were to write it here, I would say that A, acceleration, only has one component, right? So in 2 dimensions, we are going to use vectorial notations. I'm going to have an x component and a y component, an I component and a j component, right? So I'm going to use this under arrow to show a vector, right? So this acceleration how many components does it have? It has only one component in negative j direction. Therefore, and its magnitude is g, right? G, j, and I'm going to use j hat, in fact, that's easier. It's not easier, it's more common to use. And in general, I would rather follow the convention rather than inventing my own. So negative g, j hat. So right now we're just trying to analyze this problem, understand the physics, right? So A is always this. All right. So in general, if you think about it in kinematics problems, we have velocity, we have acceleration, we have velocity, and we have displacement. So every single problem we have acceleration, velocity, displacement, and time. That's it. Right? All right. Do we know what the initial velocity is? Yes, we know it's 10 meters per second. Do we know the launch angle? Yes, we know that. So, I'm going to describe velocity in this form. I'm going to say V0, showing that velocity at launch is V0, this is speed, cosine theta 0, I hat, right, plus V0 sine theta 0, j hat. And why is that? Because when we say the launch angle is theta 0, it means that this is my velocity, and this is theta 0. Right? So V0 cosine this angle gives me the x component along I, and V0 sine of this angle gives me the j component. And because I placed my reference frame at this point, what is my position? It's 0i plus 0j, right? It's a choice. I placed my coordinate frame at this point and made it easy for myself. You could have chosen any other point, but our goal is to analyze the physics. So we would like to understand the physics, and it's easier to understand the physics if we place our coordinate frame, the origin of our coordinate frame at this point. All right, so I have position, initial velocity. Acceleration, in fact, it's not just initial acceleration. Acceleration is always negative gj at any point on this path. All right. Now, what we are looking for is, we are in fact looking for And let me even make it easier, because I think if I use X, it would be a little bit confusing here. So I'm going to use R. I apologize. This is R. Initial position. I apologize. Because if I use X, I'm going to confuse you with X, because you normally use X for horizontal position. So I'm going to use R. This is R0. So now, what the problem is asking us is essentially R1, right? Because, all right, let's go back here. Now, what is it that the problem is? That what's our unknown? Unknown. That's our next question. So what we did was we analyzed the problem, and we essentially put it in mathematical form, the information we have. So we know everything about initial position, initial velocity, and acceleration. All right. What we are looking for, our unknown, is R at 1. This is unknown. And then we're also looking for the time. All right. So then again, so go back to the basics. So if you know how to approach this problem, if I say R1, you know where it comes from, like you can immediately imagine or at how to compute R1, that's perfect. But if you have problems with that, you should think about it this way. You know the initial displacement, initial position, initial velocity, and acceleration. And you have to think about our kinematic relationships. So what do we know in 2 dimensions? Or in general, for projectile motion in 2D, what is it that we know? Had I asked you to write, for example, compute the displacement in vertical direction, how would you do that? Or in general, if I ask you for point mass to compute the position, how would you do that? You would say, in general, this is what I would do. I would say any R is equal to R0 plus V multiplying by T plus half acceleration times squared, right? Because that's the equation we have. What is the other equation we have? So all right, so let's see what we have here. Before I go to the next equation and make it more complicated, this is the fundamental equation you have already seen in high school, in the first course, in physics, in dynamics, in university. What I want to do is, I want to apply this equation. That's the only equation I have for this problem. And I want to apply it between these 2 points, R1 and R0. And to make it easier, I'm going to apply this equation separately to this direction and this direction, right? Because at the end of the day, R has 2 components. R has I component and J component. And if you wanted to do it all at once, by all means, you can do that. But I'm going to make it easier. So, in vertical direction, this is what I have. I have minus y1 equals y0 plus v0 sine theta 0 t, right? Plus or minus half gt squared. Why? Because point 1 has a height y1, negative y1, because positive axis points up. So I have negative y1 for this point. Then we have y0 plus velocity in this direction. I have v0 sine theta 0 t plus half acceleration in this direction. Again, g is negative because g points down, time squared. And this you can easily and quickly identify this equation and see that this is a simple projectile motion, and therefore you can easily understand this equation. All right, so let's see what we have here. We have y1. This is what we are looking for essentially. How far below the launch level does the jumper land? You have y0. What is y0? y0 is equal to 0. Do we have v0? Yes, we do. We have sine theta 0? Yes, we do. How about time? It is unknown. So time is unknown, and this is unknown. G is known, gravitational acceleration on ground. So we have two unknowns and one equation. Right? Great. So let's call this equation 1. Now, I'm going to apply the same equation to horizontal direction. In horizontal direction, do we have any acceleration? No. If we had any acceleration, we would have been given that. In horizontal direction, there is no acceleration. A goes to 0. Therefore, it's super easy. So, for this point, and this is my x1, all right, x1 in horizontal direction, I have x1 is equal to x0 plus v0 cosine theta 0 t. And what is x0? Again, this is 0. All right. So time is unknown here. How about x1? x1 is also unknown. Now I have two equations and three unknowns. You can quickly get to the point that, all right, so we need an extra equation, auxiliary equation, because we're missing that. Where do we get that? Now think about it for a moment. So I have an equation for y1, an equation for x1. If you go back and read the problem carefully, what else do we have? We have alpha. Is there any way to use alpha? Yes, we can use alpha by saying tan alpha is y1 over x1. And this is equation 3. So, 3 unknowns and 3 equations. So you can easily solve this equation. This is super easy for you now, because you can easily, for example, out of many ways you can solve this problem. You could say, all right, from 3, y1 is x1 tan alpha. All right, and from 2, x1 is v0 cosine 0, v0 cosine theta 0, and time, so just be careful, this is how you should write it, tan alpha. And then this is 4 sub 4 into 1, and then solve for time. Then from 2, solve for x1. From 3, solve for y1. And what you're going to get is, at the end, you're going to get y1 equals to 1.42 meters, all right? And then you get x of 1 equal to, forgot, I get something like, I don't remember exactly. You can compute that. And you also get something for t, you get something around 0.7 second. Right? So now think about this problem. You can essentially expand this method and solve any two-dimensional problem in 4-point masses. All right. So email me if you have any questions. Here's my email address again: samousv@uwaterloo.ca. And I'll see you next time.